everybody, this is Unit 2, the periodic table. We are in Section 2, which is all about the different periodic trends. So you're going to be taking notes just on normal paper. I don't have guided notes for you today. And you need to have out your periodic table in front of you, preferably the one we did in class where we color-coded the group names on there. So first we're going to do a little bit of review, remembering that the periodic table is organized from left to right by the atomic number. It seems as though it should be organized by the atomic mass, but if you actually look through there are some discrepancies in that. So it's actually just the atomic number, the way that it's organized. And then we have the vertical columns called groups, also referred to as families. And within those groups, within those vertical columns, elements contain similar chemical properties. You saw some similar physical properties from the Element ID lab, and now we're going to talk about the chemical properties. The horizontal rows on the periodic table are called our periods, and depending on what column or what period or group it falls in, we see these trends from their properties. The first trend is one that every single trend after this follows. Everything is based off of this idea of nuclear charge. And we just have to remember that inside the nucleus there are protons and neutrons. So the nucleus is positively charged because it has those protons in it that are positively charged and neutrons are neutral. So we have these negative electrons outside and then these positive protons in the middle. And what happens is the negative is attracted to the positive. So we get this attraction between these electrons out here and the protons in the middle. There's an attraction between there. They want to be close to each other. So nuclear charge is related to the number of protons in the nucleus. As the proton number increases in the atom, the nuclear charge also increases, becoming more positive. So beryllium here only has 4 protons, so it has a nuclear charge of 4, or plus 4. Whereas oxygen has 8 protons, so it has a nuclear charge of plus 8. So you can see that the electrons here are more attracted to the nucleus of the oxygen because there are more protons inside the nucleus. So here's our trend for nuclear charge. As you go from left to right on the periodic table here, we have an increase in protons, and that causes an increase in nuclear charge. If you look in here, I have the explanation for why it increases or why it decreases in other cases. And then also as you go down the periodic table, if you notice, hydrogen has fewer protons than francium, so francium would have a higher nuclear charge there. So our next trend is all about shielding, which is exactly what it sounds like. Shielding, a shield, blocking, that's kind of what the thought process is here. So in an atom, I'm going to move this up a little bit. In an atom, we have the nucleus, which is positive, and then we have, let's say this is the first energy level, there's 2 electrons, and then we'll do, so this is the Bohr model for lithium, essentially. So these electrons in the center, this one and this one, these guys are repelling this electron here, because they're all negatively charged. So it's repelling that electron there, but that electron is still attracted to the nucleus because the negative electron is still attracted to the positive nucleus. So what these guys here in blue are in energy level 1, they are blocking that attraction a little bit. Not all the way, but they are blocking that attraction. They are shielding the valence electron from feeling the attraction to the nucleus. So those energy levels, the interior energy levels, all the energy levels that aren't the valence shell, act like walls to block that nuclear charge, and it reduces the attraction that the valence electron feels towards the nucleus. And here's what's going on there. As you go down the periodic table, ooh, don't like that. As you go down the periodic table, we get more and more energy levels. Energy level number 1, 2, 3, 4, so on. So each period adds an extra energy level. If we add more energy levels, we add more shielding. So we have more shielding down to the bottom, but across the top, going from left to right on the periodic table, that stays constant because we're not changing the number of shielding electrons. We're just changing the number of valence electrons. So there's no change to shielding when you go from left to right on the periodic table. So here's that image that I drew earlier where the outer valence electron is being blocked or shielded by the interior electrons, so the attraction it fields towards the nucleus is reduced. Now this one is probably our most important trend because, like I said, everything is based off of nuclear charge, but nuclear charge is impacted by shielding. Now effective nuclear charge is kind of a combo where we took the nuclear charge trend and the shielding trend and we combined it into one to see how those two cancel each other out, because they do cancel each other out a little bit. So effective nuclear charge, ENC, is the exact positive charge experienced by the valence electrons. This is less than nuclear charge due to shielding. So even if there's a crap ton of protons there, but if there's a bunch of energy levels, the energy levels are going to be shielding the valence shells, or the valence electrons. So we want to know how much attraction are the valence electrons actually feeling. And the way you do this is with a calculation. Now don't get thrown off by the fancy letters or anything. Don't get thrown off by the variables. All it is we find effective nuclear charge by figuring out the total number of protons and subtracting the interior electrons. I can find interior electrons by doing the total number of electrons minus the valence electrons. For example, let's do that lithium that we drew earlier. Lithium has 3 protons. Oops. Get out of here. Lithium has 3 protons. We know that lithium has 3 total electrons. And because lithium is in period 1, I have 1 valence electron. So I can do that as my equation, or I can simplify this down and say that there's a nuclear charge of 3 and there are 2 interior electrons. Okay, that gives me an effective nuclear charge of +1. So here's another example of that, this time with the phosphorus atom. So phosphorus has 15 total protons with a nuclear charge of 15. It also has, they calculated the interior electrons a little bit differently here. In this case, they just added them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. I don't care how you figure out the interior electrons. If you want to add them up by shell, if you want to subtract the valence electrons from the total, however you want to do that, you're going to get to the same answer. So pick one way to do it and then go with that. But either way, you should feel comfortable with knowing that the effective nuclear charge here is +5, which is very different from the 15 nuclear charge because we had that reduction of attraction from the shielding electrons. So here's the trend for that. As you go from left to right on the periodic table, we increase our nuclear charge, or our effective nuclear charge. And the reason that is because we keep adding more protons. So that means we increase our nuclear charge because we added protons. More protons, more attraction. And since all of the things across the period have the same number of energy levels, they have the same number of shielding electrons. So now shielding isn't a factor, and all we're worried about is nuclear charge, and that is why effective nuclear charge increases. Now when we're going down a group, it remains fairly constant, and here's why. Even though we keep adding a ton of protons, we are also adding more energy levels. So what happens is the nuclear charge is canceled out by the shielding. So there is really no change to effective nuclear charge as you go down a group. Here's our atomic radius. Now the atomic radius, we can't just measure it as half of the distance, as half of the diameter. You can't just measure the distance from the nucleus to the outer electrons, the valence electrons, and that's because there's really not a specific boundary to the edge of an atom. So the way we measure this in real life is we look at 2 bonded atoms, like for instance in this picture is H2, 2 hydrogen atoms, and we measure the distance from one nucleus to the next, and we divide it in 2. So the atomic radius is actually kind of an average, and that's why we can't figure it out for noble gases, because noble gases are super unreactive, so they're never going to be bonded in 2 atoms like this. They're never going to be buddied up in a way that we can figure out this distance for them. So we don't necessarily have the atomic radius of our noble gases because of the way we measure it. So the atomic radius is half the distance from the nucleus of one atom to the nucleus of another. The high effective nuclear charge causes there to be a small radius. That really means that when we have a strong attraction to the nucleus, the atom is really, really tiny. And that's because the strong attraction to the nucleus, the positive nucleus, is pulling those electrons in really, really close. So here we go with this. So as we go from left, or from right to left in this case, our atomic radius gets bigger. So on this side they are bigger than on this side. They are small. Okay? From top to bottom, they are large on bottom and small on top. So that means that fluorine here is going to be our smallest, and francium here is our largest. And here's why that is. Remember I said that a high effective nuclear charge means a small atom? Well, over here fluorine has a ton of protons with very little shielding. That gives it a big effective nuclear charge, a lot of attraction. The attraction from the positive protons are pulling in the negative electrons in really, really, really close. Whereas over here with francium, it does have a lot of protons, but the extra shielding from these 7 energy levels reduces the attraction, causing there to be really a pretty low effective nuclear charge, meaning there's not very much attraction from the electrons to the nucleus. That would cause it to have a very large atom. So just kind of browse this picture. This is the atomic radius without the transition metals, because things always get a little wonky with the transition metals, but this is the general trend across the periodic table. Now we need to move to ionic radius, and the ionic radius is the radius of an ion, and it really does depend on if you're talking about a cation, positive, or if you're talking about an anion, which is negative. So cations, they lose their valence electrons to become a positive charge. Kitty cat. Meow. Okay, so they become positive. And remember, when they lose their valence electrons, they're really getting rid of an entire energy level. And when they get rid of an entire energy level, that reduces shielding, that makes there be more attraction to the nucleus, and that attraction to the nucleus pulls the electrons in really close. So that's why over here with lithium lost an electron, it lost an energy level, and notice how much smaller the lithium ion is from the lithium atom. Same with beryllium, magnesium, and sodium. Now with the anions, what they're doing is they're gaining an electron. They gained 1 electron or 2 electrons or whatever, and that electron is going into the valence energy level. Now remember, electrons don't like each other. They don't want to be near each other. So they're going to increase the repulsion. The electrons are pushing each other away. And when the electrons push each other away, it makes the energy level actually bigger. So that's why F-1 is bigger than F. It's because of the extra repulsion from the extra electron in the energy level. So here's just an image of that. Go ahead and pause and kind of look at this, take a second, investigate it, write down any questions that you have. Up next is a chemical property, our first ionization energy. Since I'm specifically telling you this is the first ionization energy, that means that there's going to be more than one. We're going to, in this class, focus on what the first ionization energy is and just let you know that there can be more than one. So, ionization energy is a measure of the energy required to remove an electron. We are removing an electron, and when you remove an electron, you become a positive ion. We're getting rid of an electron, we're making a cation. So, it's the energy required to do that. How difficult is that to do? And therefore, the attraction between the nucleus and the outer electrons, shown in a reaction as gaseous, because of the highest energy state for a substance. So, what's going on here is if I start from a solid, the energy you first put into there is going to go into causing a phase change to happen. So, you wouldn't be getting very valid measurements because you would be using energy to change from a solid to a liquid and then from a liquid to a gas, and then the energy would be used to ionize the atom. So we use the definition of ionization energy based off of the gaseous state because we don't want to worry about changing any states of matter there. So the energy required to remove one electron from the gaseous atom in its ground state. Okay, we are going to be making sure that you don't mix this up with anything else. So I would even go start making a Quizlet now, go start making flashcards, because this one is very similar to one we're coming up against in a couple of slides. So ionization energy increases with an increase in effective nuclear charge. That means that when there is a strong attraction between the electron and the nucleus, it's really hard to pull it away. Okay, so it's like if you are, I don't know, you really like your best friend's girlfriend. You really, really like her, but they are like tight. They are like buddy. They've been dating for years. They are happy. It's going to take a lot of plotting for you to go up in there and wreck that relationship. Don't do this. This is a bad idea. But it would take a lot of energy for you to go in and wreck that relationship and steal your best friend's girlfriend. This is how you ruin lives. Don't do that. But if there wasn't very much attraction there, if they didn't really like each other, if they were fighting a lot, if they were just bad for each other, it wouldn't take as much energy to break up that relationship and steal a girlfriend or boyfriend or whatever. Don't do that. This could also work with best friends. That probably would have been a better example than it wouldn't be encouraging home wrecking. You know what? Just don't date until you're out of high school. It's not worth it. Off topic. All right, moving on. Second ionization energy would be removing another electron. So after we removed one, what if I wanted to remove another? That's a whole nother set of energy data that we're not going to get a whole lot into, but you can remove more than one electron from an atom. So remember I said that ionization energy increases when we have strong attraction. So we have strong attraction or high effective nuclear charge over on this side of the periodic table. So that means that over on this side of the periodic table, it's going to be harder to remove an electron. That makes sense. These guys want to be negative. They really don't want you to make them positive. These guys want to be positive. Therefore, they're happy to give up an electron. Okay, and down here, remember, francium has a whole bunch of energy levels which are shielding the attraction between the nucleus. So because francium has a whole bunch of energy levels, there's not a whole lot of attraction there. That would be your long distance relationship. You know, you move across country or whatever, it's a lot harder to maintain a relationship, a friendship, whatever. So here's just kind of a color-coded image of this to show you the ionization energy. And notice there are a few that don't follow this trend as perfectly as others. These are just a general trend. They're not perfect, exact, every single element follows this every single time. But you can kind of get a gist of what's going on here. The next one up is our electronegativity. So electronegativity is the ability of an atom in a compound to attract the electrons from another atom. So in this case, in this picture, we've got a chlorine atom that looks really mean and scary. Okay, we got a chlorine atom here, and we have a hydrogen atom here. And you can tell that chlorine is able to attract these electrons more towards it than hydrogen is. Hydrogen is not very good at keeping the electrons. Now let's talk about why that is. Chlorine is on the right side of the periodic table. Chlorine has a lot of protons. It doesn't have very much shielding. That means it has a high effective nuclear charge and a strong attraction to the nucleus. So that means that chlorine has a very positive nucleus. It's really attracted to these electrons. Whereas hydrogen, poor little hydrogen, only has one proton. It sure doesn't have a lot of shielding, so that's nice, but it also doesn't have a lot of protons, so it's a lot weaker. So that doesn't mean that chlorine's going to steal the electrons away because we're still in a chemical bond, but chlorine is going to hold the electrons closer to it than hydrogen, and poor little hydrogen is just hanging on for dear life there. So here's the trend for that. Go ahead and write down any questions that you have from this. Make sure you come with questions. Don't come with, I don't get it, I have no idea. Like, come with a specific question to ask me next class, but we are going to do a bunch of practice with this, so don't freak out.